Okay, we've been dealing with straight line motion. Now we're going to look at circular motion. Need to define a few things, of course. So angular velocity, well, if I've got a circle and we're rotating in our circle, so a point will move from A to P. Now when it does that, it'll sweep out an angle at the centre. And so the rate of change of the angle is the angular velocity. Often we symbolise that with omega, or it could be theta to t, or using Newton's notation, it could be theta with a dot on top. We measure it in radians per second usually. I suppose it could be another time unit, but you'll find that most of this stuff is radians per second. So all right, how do we convert it into a linear velocity, also known as tangential velocity? And the reason it's called tangential velocity, I guess, the way I kind of always imagine it is, well, if I'm going around a circle and say it's attached to the centre of the string, if I was to cut that string, it would fly off at a tangent to the circle, so hence tangential velocity. So the linear velocity, it'll go at whatever angle the tangent at that instant is making, and it'll have velocity v. So the question is, how do we work out this velocity v? Well, we know the length of the arc AP, we're going to call that x. Now x, you'll remember, is r times theta. So dx to t will equal r times the theta to t, and there we go, we've got our conversion. So the velocity is r times omega, or r times theta dot, whichever way you prefer to write it. Now the period, kind of nice, it stays the same as what we had for simple harmonic motion. And it's not a coincidence, because circular motion is simple harmonic motion. If you imagine it was moving in a horizontal circle and you're just looking at that circle, I mean, you wouldn't see it travelling in a circle. What you'd see is an object going backwards and forwards, and it would be in simple harmonic motion. So as I say, no coincidence, 2 pi over omega. All right, so our satellite up there in the sky somewhere, it's got a circular orbit of 20 revolutions per day, so find that in radians per second. So all right, that's 20 times 2 pi radians per day, which then if I divide it by 24 times 60 times 60, it will give me radians per second. We end up with pi on 2,160 radians per second. Well, imagine it's 9,000 kilometres above us. I think that's around about right. It's about 8 point something. Does anyone know that? The radius of the orbit of satellites? Anyway, let's get back to our question. Let's say our one's moving with a radius of 9,000. So its radius is 9,000 kilometres. How fast is that in kilometres per hour? So we can get a feel for how fast it's actually going. Well, it's going to be r times omega. We just worked out it was pi on 2,160. If we multiply that, you'll see it's going incredibly fast. So, and that's all I'm going to do today. So the first bit really is just having a think about circular motion, using that conversion rate before we get into the real good stuff. Okay.